All right, so this is the last section, the sixth section in the preparatory chapter to pre-calculus, and we're going to discuss square roots now, as we're going to be looking at them. So rational expressions and radicals. Any square roots, actually any kind of root, define and evaluating nth root. Then how do we add, subtract, multiply, divide radicals, and then eventually how do we deal with them in fraction form. And so then we're going to look at one last thing. It's called the rational exponents, fractions in the exponent. So let's begin here. The introduction to the book, I thought it was a neat little example here. Friction in tap water. How does a cold water faucet work so that the water stays sort of like in the same let's see, in the same form, I guess. Maybe that would be a good way to do it. And then at the same time, understanding that water flows very fast at certain places there. So I wanted to get a video for it. It didn't work, but the water flow video, I just couldn't get it off of YouTube here. But I did get the airflow video. So this is Bernoulli's airflow video. I thought that was kind of interesting. This person is setting up a little problem. Same thing as the water, but he's just going to use air. So he sets this up first of all. And let me get to the video where he actually starts doing stuff with it here. He clamps it down. He's going to hook up a vacuum, which is blowing air into that little hole there. And of course, the hole is made in a certain way as to conform to the Bernoulli principle. And he lets go of a ball. And let's see what happens here. The ball is flowing into the airflow. Notice it cannot get out of that airflow. And so, yeah, it's really levitating, this. And then he does a few other little tricks here. Yeah, how about a sheet of, looks like a little cardboard. And there's enough pressure there to stabilize it completely. I thought the next one was pretty cool. And I don't know if you got that. Let's go back to this one here. Let me pause it. And so there's air flowing out of here. But what's happening is the air's flowing out. There's just enough of friction to give it to levitate it a few inches above the piece here. So there's enough flow coming around. As it comes around here, it's actually keeping it. So it's almost like a flow out and a flow on top. So it keeps it stable and looks like an inch or so above where the air's coming out from. He does the same thing from the bottom, which I thought was a little more impressive here. Again, airflow is coming out this way, and as airflow is coming out this way, it's going to leave about an inch and a half space. And so the water's flowing out of here. So you could tell by these little feathers here, the water's flowing out. It's flowing this way, you can see it. So the Bernoulli effect says that air is going to tie around here real quick here, so it keeps this stable. In fact, he's going to turn off the vacuum. Let's see what happens when he turns off the vacuum. Everything falls apart, which I thought that was pretty cool. So airflow, there's a whole bunch of things to airflow, how it works. That's the reason why you can actually fly an airplane, because of the Bernoulli airflow principle. Anyways, enough of the good stuff there. Let's go to defining what in the world is a square root. It just means this: a square root of a is equal to b if and only if you can square the b value and get back to a. Only thing that we know, well, we know a few things here, but one of the things that we know from this is there's two numbers that do it. So let's say if we have the square root of 25, we say it's equal to 5. Also, the square root of 25, isn't it also equal to a negative 5? Because if you take 5 and square it, you'd get 25. If you take negative 5 and square that, you also get 25. So there's a little condition. Condition is that b actually has to be greater than or equal to 0. So we can only choose this one. Oh, sorry, not this one. This is the 5 that we choose in order to have that. So we actually call this guy something called the principal square root, and really just means it's the non-negative root, or we take the positive number or 0. We don't use the negative number in this process. All right, some more definitions here. The radicand, that is the part that's actually inside the radical. And then we have something called the radical. The radical is just that symbol right here. We can call it a square root, third root, fourth root, fifth root, cube root, but in the general context it is called the radical. Alright, so a few little properties here. And again, you will need these for calculus. This particular one you'll need for calculus here. So absolute value is actually, or the square root of x squared is actually equal to the absolute value of x. Those two are exactly the same. Isn't that kind of weird? Take a look at some numbers if you like. Just plug in a whole bunch of numbers. Plug in a 5 in there. Plug in -5. Plug in a 7. -7. See what you get out of that. Okay. And then for all non-negative numbers, if you understand that this is either a 0 or a positive number, then this applies. You could take the square root of something, square it, and it'll give you that same number back. Again, something that might just be of use to you as you are in calculus. Alright, let's jump to some practice problems here. I'll give you guys a few seconds here. Try it yourself. All yours, always. I'm going to pause the recording. Alright, so square root of 144, that would obviously be a 12, and the reason for it, I'm going to do it the way the book does it, because if you take 12 and you square it, it gets you the absolute value of 12, is that right? According to the little principle that we just studied. And that actually would turn into a 12. So again, just sort of going by the book, understanding that square root of 144 is 12. But understand this little process. It's because it's a perfect square, and then we're still taking a square root. According to the property from the last slide, it's going to be the absolute value of 12, which eventually becomes 12. Okay, how about this one? The square root of 140 over 49 technically is going to be the square root of 1 over 7 squared, according to the property on the last slide. That's going to be the absolute value of 1/7, and eventually going to be 1/7. Alright, how about this one? Alright, how about we do it again according to this little property here. So what is being squared to give you 4/64? Looks like 2/8, isn't it? And then that really becomes the absolute value of 2/8, and that really becomes just 2/8, and in its reduced form gives you 1/4. And of course, students say, Mr. H, why do it that way if you can actually already reduce? Yes, absolutely, you can reduce that. 4/64 is really the same thing as 1/16, and the square root of 1/4 being squared gives you 1/16, which really is the absolute value of 1/4, which then really is 1/4. So same thing on that side as well. Okay, some more properties here to take a look at. Again, if these are positive, then we can do this here. If A and B are both positive, I can either multiply the numbers together, take the square root, or I can take the square root of the numbers individually and then multiply them together later. Again, same thing, division. I can divide first, then take the square root, or take the square root of those numbers and then divide them. So practicing that concept. And why do we need that concept is because whenever we simplify radicals, this is the algebra way of doing it. And again, there's some fast shortcuts. There's doing factor trees. There's pulling out prime numbers out of here. The proper mathematical way of doing it is to say this here. 20 is really technically the square root of 4 times 5. And reason why we want to use the 4, because 4 is a perfect square. So that means I can split this off two different pieces here. So really this is the square root of 4 times the square root of 5. And then we know that the square root of 4 is 2, so then it's 2 radical 5. Again, we're just simplifying it. I just want to show you, I think we do that in our heads real quick here, right? Don't we? Like, we say, oh yeah, that's 4 times 5, so that means that becomes a 2, so it's 2 radical 5. Alright, but again, just working with the principle here. On this case, square root of 6 times square root of 8, what we can do is we can multiply these guys together, gives you a square root of 48. And as we think about what's the biggest square root that multiplies to give you 48? Of course, 4 would do it. 16, I think, yeah, 16, isn't it? 16 times 3, so 48 is really 16 times 3. In that case, we can split off the 16 and the 3 into individual square roots, and then we got ourselves a 4 root 3 on there. Again, just looking at the principle itself, right? Okay, let's put in variables now. How do we work with variables? Somewhat the same way. So the square root of 12 times x squared. We're going to pull out the perfect square out of here. And again, we can probably do this in our heads here. But 12 can reduce down into 4 times 3, 4 being the perfect square. We also have this little extra x squared. So now let's move all the perfect squares to the front. So how about a 4x squared goes to the front? The leftovers would be the 3. Splitting it off into two individual pieces, 4x squared in one, a 3 in the other. And now taking the square root of 4x squared, we've got a little bit of problem here because that little x right here. We're not told that x is greater than or equal to 0. So we assume this could be a negative, a positive, a 0, whatever. So the 4 does become a 2 on the outside, but we've got to be careful here because that will become a square root of x. And again, it's the principle that we covered in the previous slide. And then we have that little leftover of 3. So kind of careful there. You can write it like this. Other math textbooks, just depending how they work, they could write it. They write the absolute value at the end. It doesn't matter. Either or is just fine. On the other side, let's see if we can put this together. Looking at this here, what I'm going to do, I'm going to split this off since I can't really solve. There's nothing. 20 and 27 don't reduce. So what I'm going to do, I'm going to use a little principle about division. I can split this off into a top and bottom, and I can do then the work individually. Okay, in this case, keep on going here. So let's see, 20 will reduce down to a 4 and a 5, and then also you have this x cubed. So I'm looking for perfect squares. Let's see if this makes sense. I'm going to split this off into a 4y squared. There's my perfect square. Times my leftovers, which is a 5, because that's not a perfect square. And then there's the extra y to give me y to the third. On this one, 27. 27 is, let's see, perfect square is a 9 and a 3. So how about a 9x squared goes to the front, and then you got the little extra little 3 on the back. Alright, and then let's simplify this here. So how about a 2 absolute value of y, just like we saw over here with the x, leftovers 5y, on the bottom 3 absolute value of x, square root of 3. And now let's look at our domain restrictions. It says x cannot be equal to 0. Well, that's okay. It can't be, because if this is 0, that means we would be dividing by 0. Then we're in trouble. Okay, but I got another domain restriction, that y is greater than or equal to 0. So if y is greater than or equal to 0, technically this absolute value symbol is actually useless. So the simplified version of this is a 2y square root of 5y over 3 absolute value of x, because we don't know what x is. We don't know if it's negative or positive. And there's my final answer. So kind of be mindful of that whole domain issues here. That might be an issue to think through as well. Alright, again, there's little warning symbols here. Important little fact that some students forget is this concept right here. That is not true. Absolute value of a plus b is not equal to the absolute value of a plus the absolute value of b. That doesn't make sense. Same thing here, is that doesn't make sense either. Okay, in fact, let me actually highlight those as opposed to putting something around them. I think I prefer the highlighter tool here. That one and this one. There's our little warning problem stuff. Okay, cool. Let's go on. We're going to skip. Boom. We're going to skip practice problem number 3. It was that whole calculation of water flow. If you want to look at it, absolutely go for it here. It's going to take too much time for us to do so. But if some general principles for nth roots. So again, could be to the 3rd, to the 4th, to the 5th, to the 6th. It doesn't matter, but here's some general principles to guide us. and then we'll take a look at some practice problems. If a is positive, so if we know that for sure, and we're taking the nth root of a, and we know that is equal to b, then we know that b to the n is equal to a. And then we also know that b itself has to be greater than 0. So if a is negative, then the nth, and n is odd only. If n is odd, then nth root of a is equal to b, as long as b to the n is equal to a. So this just means that if you have like something like the cube root of something, or the fifth root of something, even if it's a negative or a positive, I'm just going to put a random number in here, 1625. I can still get answers here. This is if a is negative and n is even, then it's not a real number. And I think we already know this here. If you're just taking a square root of a negative 27, we say not a real number. All right, if it's a odd root, I can still keep the negatives in there. If it's a even root, even the fourth root of a negative 16, again, it's going to be that, because there's no way I can multiply 4 times a number itself to give you a negative number. It doesn't work. Okay, and the last one here, if a is equal to 0, any root, doesn't matter what it is, 5th root, 28th root, 28th root of 0 still be 0. Okay, there's some general principles. Let's jump to some practice problems here for you guys, all yours. Give you guys a minute or so, try it yourself. Okay, the cube root of negative 8. That will be a negative 2, because negative 2 times negative 2 times negative 2 would produce that negative 8. Okay, cube root of 5, oh sorry, 5th root of 32, sorry, that would be a 2. 4th root of 81, that would be a 3, again, because 3 times 3 times 3 times 3 is 81. And then the 6th root of negative 4, we say not a real number. You can't take an even root of a negative number. Okay, some more principles from algebra here. If n is odd, and you're taking the nth root and you're taking it to the nth power, this will work for negatives and positives alike. It doesn't really matter if it's a negative or positive. Let's maybe take a look at one example here. So, cube root of 2 to the 3rd. If we do this here, you're going to take 2 times 2 times 2, which is 8, and the cube root of 8 we just saw last time is just 2. So notice this number is exactly the same. Let's do this again with a negative 2. What's going to happen here? So negative 2 times negative 2 times negative 2 makes a negative 8, and cube root of negative 8 is still a negative 2. Notice the numbers are exactly the same. That's for the odd. If it's even, then we got ourselves a little problem. Because if I take the, say, the square root of 5 being squared, well, that's going to give me square root of 25, and square root of 25 is just giving me a 5. So in this case, that's true. What happens if I'm taking the square root of a negative 5 being squared? Well, that's going to be a positive 25, because if you take even powers of a negative number, the negative disappears and you get yourself a 5. Okay, so we have this little rule then. If that's the case, then why do all the work if you go like this? You can just say, oh, you know what? I'm going to take the, since I'm taking the square root, I'm taking the second power of negative 5, I'm going to take the absolute value of it, which would just give me 5. Good there. All right, let's jump to a few more here. And then this is now the product and quotient. It just means that if you multiply numbers, any kind of root would work. So multiplying numbers inside the radical first, or taking the radical first, then multiplying the numbers, doesn't matter. Again, we saw this with square roots. So now we're extending it to any kind of root, any kind of nth root. Same thing here. Division first, then taking the nth root, or simplifying first and then taking the nth root will produce the same exact answer. All right. So let's take a look at some practice problems here. Again, all yours to try yourself if you can. And if you can't, wait for me. We'll do it together. All right, what I find sort of maybe at least helpful if you want to do this here is to write down all the perfect cubes, because I think we're pretty sure aware of perfect squares, right? We can do 0, 4, 9, 16, but perfect cubes here. So I wanted to list them for you. How about 1 is a perfect cube? 1 is a perfect everything here. 8, 27, 64, 125, 216, and 343. I will let you think about what number being squared will produce those numbers. Okay, and then maybe like fourth roots, fourth powers, I think. So if you take 1 to the 4th power, stays a 1. If you take 2 to the 4th power, it would be 16. And again, perfect fourth powers would be 81, 256, and 625. And those are really the ones you'll see in this class. So at least list them for you. Okay, so now the name of the game is 72. What cube of these guys multiply some kind of other number to give you a 72? And it's going to be an 8, because 8 times 9 is 72. And again, we can split it off into 2 different pieces here. And this is a perfect cube root of 2. And then the leftovers go inside here. Notice that 9 is a perfect square. That's great, but we're not looking for perfect squares, we're looking for perfect cubes, and 9 is not a perfect cube. Okay, this one, now with variables in it as well. So 48, I need a number here that multiplies to give you 48. 16 times 3. So let's go for it here. So 16. Now notice the a squared. A squared, that is a perfect square, except we're not looking for perfect squares, we're looking for a perfect fourth root. So now I want a 4th power in here. It's not here, it's actually lower than that. So I'm going to leave it as a leftover piece. So splitting it off into 4th root of 16 times 4th root of 3a squared. And how about a 2 on the outside? Because 2 times 2 times 2 times 2 gives you 16, and the leftovers would be 3a squared. Make sure you always put the index of 4 or index of 3. If it's a square root, you don't need to. But if you don't do this, then we think it's a square root, and that's not good. It is actually a 4th root. You have to indicate which root it is. Okay, so let's jump to a review of adding, subtracting as well here. Radical expressions here. So if you are to add 3 square root of 12 and 7 square root of 3. Remember, in order to add these up, the radicals have to be exactly the same. If they're not, you can't do that. So then we have to simplify this. And again, you don't have to follow all the steps that I do. If you know how to simplify this in one single step, let's go for it. I'm going to show you all the different steps in case you're a little stuck here. So 12 is really 4 times 3. And then 4 breaks down into a 4 and a 3 by themselves. And then this technically becomes a 2. Now it's a multiplier of 2 to the 3 in front. And now we have a 6. Radical 3 plus 7 radical 3. Notice now the radicals are exactly the same, so finally I get to add them up. And I only add up the coefficients. I only add the numbers on the outside. So 13 radical 3. Hopefully you got that one correct. And if you did, that's good, because here is a more complicated one. So again, give you guys a minute by yourself, try it yourself. See if you can do it. All right, a lot of stuff in here. So let's work our way through it here. So first of all, is I want to take out from here, I want to split this off into its perfect cube component. And think about perfect cubes here. With 135, I wonder what's a perfect cube there. So 2 on the outside. Oh, you know, how about this? Let's break 135 into its pieces here. So 135 is really 5 times 27. Okay, you know it's going to divide by 5 because 5 at the end. And there it is. 27 is that perfect cube because it's a perfect cube of 3's. So there's my factor tree, bringing out this 3, 3, 3 combo. Awesome, so let's go for it. So that's 2, radical 3, cubed times 5x, which is a leftover piece. All right, got to do the 40 as well. So if you want to do it the way I did it, that's fine too. But I think we can figure out, let's see, isn't it 8 times 5? 8 times 5 is 40, and 8 is really 2 to the third. So how about a 5x that's left over? Okay, splitting it off. And again, this is just going to produce a 3 on the outside, right? So why go through all the mess splitting everything off? How about just a 3 here? Leftovers give you that 5x. Over here, you know it's going to be a 2 because you're going to multiply to 8, and the cube root of 8 is back to 2. So how about a 2 on the outside? Cube root of 5x on the inside still. Multiplying these guys together gives you a 6 in front. Over here also gives you a 6 in front. How funny. Okay, so if you have this, subtract this. Since the radicals are exactly the same, we can subtract them. But since the outside numbers are exactly the same, 6 minus 6 is going to be a 0. So technically this just becomes a 0. All right, the warning sign again. All right. I guess I should highlight these here. So real quick here, if the numbers inside the radical are different, they cannot be added together ever. They stay separated. If you have two radicals that are exactly the same, then the answer is there's just a 2, because it's technically one of these plus another one of these makes 2 of these. Okay. All right, if the indexes, one is an n, index of n, the other one's an index of m. If the indexes are different but the numbers inside are still the same, still you can't be adding them because the index has to be the same and the radicand has to be the same. Okay. All right, let's try it here then. Some more practice problems here for you. Okay, now the question is, can I write this as a single radical? Is it possible to do so? Well, remember we can't multiply these together because they're different radicals, but I still want to simplify this. So eventually I do want the same radical here. How do I do it? Okay. So we've got to think of a number that 5, oh, this is actually a square root, isn't it? So technically there's like a little 2 right here. So if I write this out by itself, how about square root of 3 is technically, there's like a little 2 right here. So now the question is, what's the number that 5 goes into and 2 goes into evenly? What's the number that 5 goes into and 2 goes into evenly? That's going to be a 10. So here's what I want to do. I want to convert this, instead of a square root, I want to convert it into a 10th root. The way I do it, I make an index of 5 over here. So notice it's going to be 2 times 5. At the same time, what I'm going to do, I'm going to take this guy to a power of 5. So really I'm taking a 5th root and a 5th power. 5th root, 5th power. And what that allows me to do is to have a index of 10 on the outside and 3 to the 5th on the inside. Okay, I got that one to index of 10. Now I got to go back and do this 5 radical 2, and I'm going to let you guys try this yourself. Try this yourself. Can you make that into an index of 10? Alright, again, in order to do so, you would have to multiply the 5 by 2, so then hence what you're doing is you're taking an extra square root into here. To combat that, you're going to have to square the inside, so these guys don't change at all. Okay, that becomes, looks like 10 radical 2 squared, and now let's go back to the beginning here. So this right here, the initial problem, now has become 10 radical of 3 to the 5th times 10 index of 10 2 to the 2nd. And of course we have to multiply this all out. We can't really just leave it like this. We actually have to figure out what that is. So anybody, what's 3 times 3 times 3 times 3 times 3? And off to the side here, you're going to have to know it. but I get 243. 2 squared is a 4, and let's multiply these guys together because that's what we need to do. So that's 12, that's 17, that's going to be a 9. So I got the 10th root of 972 as my final answer. Okay, hopefully that may be something new for you guys from algebra here. Hopefully you saw that before, but if not, there it is. Okay, then we have something called rationalizing the denominator. And rationalizing the denominator, you have learned that you cannot have a radical on the bottom. You cannot have a radical in your denominator. We're trying to get rid of this little radical symbol here. Well, that's true 95% of the time. Every once in a while, what we actually want to do is rationalize the numerator. So we'll work with both, because you should be able to do both. Sometimes we don't want the radical on the bottom. Most of the time we don't. Every once in a while we actually don't want a radical on top, because if we do it, then it becomes a very complicated number. Anyways, let's go for it here. So 7 divided by radical 8. I want to get rid of this radical. First of all, can I simplify the square root of 8? Yeah, it's actually 4 times 2, which really becomes 2 on the outside and radical 2 on the inside. So simplifying as much as we can. And now we have to get rid of this radical. The way we do it is we multiply through by forming a perfect square. So if there's a 2 here, I need another 2 to make a 4. Because now that's a 4. Square root of 4 is but 2. So how about 7 radical 2 on top? This 2 comes from here. And this 2 is really the square root of 4 that has now been simplified down to a 2. And final answer, how about 7 radical 2 over 4 as our final answer. Okay, for square roots, let me warn you real quick here. For square roots, what we do is we just multiply by the exact same number. And the reason why we do it is because in order to form a perfect square, we just need the exact same, we need another one of the exact same. So if this was maybe square root of 5, all we need is we know multiply by another square root of 5, because it makes a square root of 25, which is a perfect square of 5. It's not so much so for cubes or 5th roots, 4th roots, 10th roots. Those are a little different, so let's take a look at those. So the question is, what should I multiply by in order to get rid of this little radical symbol on the bottom? Well, let's think about this here, because it's a little different. Since I have a 4 over here, again, it's a perfect square. It's not a perfect cube, because that's what I'm looking for. I'm looking for a perfect cube. But the question is, what do I need to multiply in order to form that perfect cube? And if I were to multiply by the square root of a cube root of 4, that would make a cube root of 16, and 16 is not a perfect cube root. That's my problem. But I'm thinking to myself, okay, 4 is really made up of a 2 and a 2. I already have 2 2's here. So really what I need is I need an extra 2 in here, because that will form a triplet. So what I'm going to do is I'm going to multiply by the cube root of 2. So now that's going to be 4 times 2 is 8, and 8 is a perfect cube. So that's, again, 2 times 2, and then now a third 2 to make it a perfect cube. Whatever I do on the bottom, I'm going to do on the top. And let's see what I got here. I got myself a cube root of 8. On top, I get myself a cube root of 6. And then again, cube root of 8, that is actually just a 2. And I've simplified it, no more radicals on the bottom. So kind of careful there. With a 4th root, again, the same thing. You want to multiply so that you get a 4 of the exact same number being multiplied together. Okay, let's get even more complicated. So far we've been dealing with a single term on the bottom. What happens if you have a binomial on the bottom? 2 terms. How do you get rid of those radicals on the bottom? And hopefully you know something called the conjugate. Remember conjugate from algebra here? We're going to multiply by the exact same thing that's on the bottom, except we're going to change the sign in the middle. So square root of 7 minus 5 is there, so we're going to multiply by square root of 7 plus 5. And why we do it? Because the middle terms are going to cancel. Technically you're going to have to do FOIL over here, but the middle terms will be gone. Alright, so all we got to do is multiply the square root of 7 times square root of 7 is just going to be a 7. And at the end, square root of 5 times square root of 5 is going to be a 5, and we're subtracting the 2. I suggest don't multiply the 2 into here right away. keep these two separate first, because 2 there, and the reason for it is because sometimes the denominator, as it is simplified, will actually cancel the original term that you had up here, or at least reduce it. In this case, this is going to cancel it. So the 2's are gone, and we're left with radical 7 plus radical 5. Okay, let's put in a variable in here. So let's see, how will this work? Alright, what do we should multiply by? We should multiply by whatever's on the bottom, except change the sign to get the conjugate. So square root of x minus square root of 2. Whatever we do on the bottom, we got to do on top as well. And so again, multiplying this around. That'll give me an x. That should give me a minus 2. On top, I'm going to hold off the multiplication just for a second here. X minus 2. We're going to multiply square root of x minus the square root of 2. And hey, we don't even need to multiply because I see something that can cancel. So how about x minus 2 cancels with x minus 2? Since we have only 1 on the bottom, no more denominator. So how about square root of x minus square root of 2 as our final answer? All right, jumping to another thing that we need to cover, something called rational exponents. We're going to do this in stages here as we build it up completely here. So first definition here, for any real number, a to the 1 over n is really just the nth root of a. So if you have a fraction in the exponent, the denominator of that fraction really is the index of your radical term. All right. So let's do some example problems just to get used to it here. So practice problem number 10. Can you evaluate this for me? 1/4 taken to the exponent of 1/2. Well, if we think about it here, this is just if we convert it. And again, if you can do it without converting, that's awesome. That's kind of where you want to be. So 1/4, and let me actually do this maybe the old style way, the full length way, and then we'll do it the shortcut way here from now on out. So 1/4 is really like this, and this exponent of 1/2 really is saying this. So you're saying we're taking the square root of 1/4. Well, the square root of 1/4 is 1/2. That's kind of what you should be thinking in your mind. But really, so you guys are sophisticated Math 15 students, you guys should say, oh, hold on, that's really technically square root of 1/4, which is really 1/2. This right here is technically this cube root of 125, and the cube root of 125, or what number multiplies itself 3 times to give you 125? It's a 5. Alright, what number multiplies itself 5 times to give you negative 32? It will be a negative 2. Okay, next, some properties here, and hopefully you guys are looking at your textbook here, because that's where I'm getting all these properties from. Alright, if a is positive, or I'm sorry, if a is greater than 0, any kind of root, any kind of nth root will always be positive. If a is less than 0, a is going to be not a real number. If it's an even root, if it's an odd root, it will just be a negative number. And then again, if a is 0, doesn't matter if it's even or odd, it will still be 0. Okay, next one. Some more properties here. Now let's extend it. Instead of just 1 over n, let's extend it to m over n. And there's 2 different ways you can write it. They're both exactly the same. Computationally, we use this one. Sometimes with variables and stuff, we use this one here. So if you have a to the m over n, again, n is the index to your root, but the m is actually your power. So n is the index, m is the power, and again, you could take the radical first and then you take the power, or you can take the power first and the radical. Doesn't matter which way you do it. Okay, but we have one little extra thing to sort of talk about, very important, especially when we start solving equations here. Let's talk about it here. And again, this is something that students miss quite often, but I want us to get it, okay? So it says, note that for m over n, the numerator m and the exponent m over n is the exponent of the radical expression. It's on page 66. You may want to just kind of read it over again just to make sure you understand this here. And the denominator n is the index of the radical. Yeah, we got that already here. So when n is even and a is less than 0, the symbol is actually not a real number. So this right here, if n is even, so a 2, a 4, a 6, 8, 10, and a is a negative number, this guy's not a real number anymore. Okay, so when rational exponents and negative denominators, such as 3 over 95, negative 2 over 97, are encountered, we use the equivalent. So again, if you have a negative on the bottom, what we do is we bring the negative to the top. If you have both negatives in the exponent, we get rid of the negatives right away before we apply the definition. Okay, so similar, we reduce the exponent to m over n to its lowest terms before applying the definition. So again, if you're taking to a power of 2/6, before you even do that, we're going to reduce this exponent down to 1/3 before we even express what we have here. So the wrong way to do it, negative 8 to the 2/6, well, we technically should have reduced this first. But if you didn't, then you would have been taking a sixth root of negative 8, which then becomes not a real number. The only problem is, if you can put this into a calculator, it actually will give you negative 2 as the answer. The reason for it is because we have to reduce the fraction to its lowest terms prior to using that definition of the exponent. So negative 8 to taken to the power of 2/6 technically is negative 8 to the 1/3, and then when you do that, you get the cube root of negative 8, which is negative 2. So this is the proper way to do it. So dealing with negatives in the exponent and reducing the exponent prior to simplifying this. Okay, of course we're going to have some problems to sort of deal with. So just kind of keep those in mind. Write them down on a sheet of paper, 3x5 card maybe, if you need to here. Anyways, let's do some problems here though. So 25 taken to the exponent of 2/3, and what I like to do, just kind of write them in radical form first, because then it gets easier. After a while, you guys will be able to do this right away. But 25 to the exponent of 2/3 technically is the cube root of 25 squared. Now, the only little issue here is that's going to be a big number here to deal with, right? So 25 times 25 is going to be cube root of 625. And if we think about that, isn't that really just the cube root of 5 to the 4th power? Alright, so with that in mind, that means I'm going to have 5 to the 3rd, and then I'm going to have an extra 5. So how about this here? 5 goes to the outside because there's 3 of them, and then you have a leftover of an extra 5 in there. Okay, so this is a process in which we took this 2 and we put it actually inside the radical. The reason why we did it, because there's really no such thing as a cube root of 25. We couldn't take a cube root of 25 directly. Now, real quick, if we go look at this one here, notice the 2 is on the inside here. So can you take a square root of 36? Yeah, you could take a square root of 36. Okay, so let's do this way here. So let's do it the other way. And what I mean by other way, let me just go back to it here. So for the first problem, what we did is we did it this way, right here. We took the 3 here, the 5, the 25 was right here, and then the 2 was here. On this one, what we're going to do is we're going to take, notice there's no parenthesis around here either. There's no parenthesis around the negative 36, so the negative is just sort of out in front. So we're taking really the square root of 26, and we're going to take that to the third power. Notice because 36 is actually a perfect square of something, we're going to do this right here. We're going to take the power later. So square root of 36 technically is just a 6, and 6 taken to the third power becomes 6 times 6 times 6, or 216, and we're done. So there's two different ways to deal with it. After you practice it a little bit, I think you'll figure out which one you want to do. But really, the hint is if the denominator, which is the index, works well with this number, that's fine. If not, then you do it according to a different form. Okay, next. Let's put in some negatives in the exponent. I think you know what negatives mean. Something about reciprocals, is that right? So 16 taken to the exponent of negative 5 halves. Well, we've got a little problem, a little negative right there. So negative exponents means reciprocal. So if I'm going to deal with this little negative right away here. So reciprocal of 16 will be 1 over 16. And then that changes into a positive exponent. Okay, so now the question is this. This technically is a square root, right? Square root. So can I take a square root of 1/16? What's the square root of 1/16? Hey, cool, 1/4. Okay. And since 1/4 is there, now I'm going to take 1/4 to the 5th power. So 1 times 1 times 1 times 1 times 1 still is 1. And anybody, what is 4 times 4 times 4 times 4 times 4? And I get 1024 is correct. Good there. Okay, again, just dealing with this here. B, let's deal with this. Negative 36 in parentheses now, taken to the negative 1/2. So first of all, I'm going to deal with this little negative issue in the exponent. And I'm going to take the reciprocal of negative 1/36. So whenever we take a reciprocal of a negative number, what we typically do is we leave the negative out on top. So leave the negative there on top. All right, what we want to do here is we want to take the, hey, this is a square root, isn't it? Square root of a negative 1/36. Square root of 1/36, negative 1/36. You can't have it because you can't take square roots of negative numbers. So the answer is not a real number. Okay, so we've come to the point here of just reviewing all the exponent rules we have. So properties of rational exponents here, and then again, this is just a quick reminder. This is stuff we've covered in algebra. Here's the exponent rules. Remember, if you want to multiply numbers with the same base, all you really got to do is add the exponents. If you want to take powers of powers, all you got to do is multiply the powers. Or if you want to take an exponent of a base that already has an exponent, you can just multiply the exponents. All right, if you have two things that are multiplying each other and you're taking powers, the power extends to each individual piece. All right, dividing numbers with the same base, all you gotta do is subtract exponents. Taking powers of a fraction, you gotta take the powers of the numerator as well as the denominator. Again, here's our definition here of reciprocal. Any number to the negative power is really the reciprocal. Again, with a fraction, you know, take the reciprocal of fractions, all we do is we change the numerator and denominator. Again, those are all rules that you have learned in algebra. Okay, jumping to this right here. So can you express for me this in its most simplest terms? All right, let's go for it here. So 4x to the 1/2 exponent times 3x to the 1/5. So first of all, we have to understand there's no parentheses around here. So that means this 1/2 exponent only applies to the x. This 1/5 exponent only applies to the x over here. So really, it's 4 times 3, which is 12. And then we'll have this little issue here. We're multiplying a base of x. So therefore, we're going to add the exponents. So 1/2 plus 1/5. If that's the case, we have to get common denominator. So the 12 is still there. Common denominator is 10. So how about 5/10 and 2/10? And how about eventually we get 12 times x to the 7/10, and there it is. There's the simplified version of that expression. Okay, of course got some other ones for you here. We'll be practicing with this. And if you got it, try it yourself, go for it. And if you don't quite have it, wait for me, we'll do it together. All right, with this one here, first of all, the coefficients themselves, 5 divided by 5 is just a 5. And I have x over here, and I'm dividing the numbers, the bases, therefore I'm going to be subtracting the exponents. So negative 1/4 subtract 1/3, common denominator would be a 12. So how about a negative 3/12 subtract 4/12? Or what we can do is we can just add the opposite. And how about 5x to the negative 7/12? Now the only little problem, whenever we talk about simplified with rational expressions or exponents, we can't have negatives in the exponent because that's not considered simplified yet. So we have a 5 here, x. The negative 7/12 is only acting on this x. So that's in that case, we have to take the reciprocal of x. So the 5 stays on top, but the x goes down to the bottom, and that allows us to change the sign on the exponent, and now we are done. Okay, and again, another one here to try, letter C. Can you simplify this? Give you a little bit of time, and then we'll do it together. All right, so let's try this here. So first things first, if you remember your exponent rules from algebra, these two have to multiply each other. And so as we look at this here, 2/3 times a negative 1/5 technically just becomes a negative 2/15. And again, this little negative comes up, so we have to take the reciprocal of x. So since there's nothing left on top, we have to put a 1. And how about x to the 2/15 as our final answer? Okay, so let's just do a few practice problems here towards the end here. Can you simplify this? Give you guys a minute each. Try it yourself. If you can't, then we'll do it together. All right, simplifying 6th root of x to the 4th. Now, it looks like it's simplified except for the fact that these two are divisible by 2. So the way we simplify this now is we say, okay, let's put it into this rational exponent form. So since 4 is the power, it goes on top. 6 is the index of our root, it goes down to the bottom, and we notice, hey, I can simplify that down to 2/3. Putting it back into its order, that means really we're looking at the cube root of x squared. There's my simplified version. So again, simplified version means the index and the power are, we call it relatively prime, which means you can't reduce the two into each other. Okay, of course, there's a little shorthand right of doing this here. The short little cut of doing this is the mathematically correct process of doing it, but we can also do this here. We look at 6 and the 4, we say, hey, that's divisible by 2, 4 is divisible by 2, therefore we have this. And that's, again, that's a little more of a shortcut version of getting to that answer. Okay, how about another one here? How about B? Can you simplify this? All right, let me try it as well here. So first of all, the indexes are different. This is a 4th root of 25. This is a square root of 5, so I can't just multiply across. So let's convert this into rational exponents. Technically, this means 25 to the 1/4. The other one means 5 to the 1/2. Well, you still can't put things together because you still have to have the same base. But I know that 25 is actually 5 squared. So this really means 5 squared to the 1/4 times 5 to the 1/2. So let's simplify this some more. What happens if we have an exponent inside a parenthesis, exponent outside a parenthesis? We're going to multiply these guys together. It really gives us 2/4, which then the 2/4 really reduce down to a 1/2. So we really have 5 to the 1/2 times 5 to the 1/2. But whenever we multiply numbers, all we got to do is add the exponents. So in this case, it's going to be 1/2 plus another 1/2 makes 5 to the 1, and we really don't write 1s in the exponent, so therefore it's just a 5 by itself. Okay, so that's another type you might encounter. You probably will encounter in calculus. How about this one? Multiple indexes, or we call it nested radicals. So you got a radical that's actually inside another radical. And so how do we deal with this? Let's go for it. So first of all, let's forget about this little radical on the outside. Let's just concentrate on this one right here. So I see a power of 12, index of 3. So if that's the case, I'm going to convert this into rational exponent form, which makes a 12 on top, 3 on the bottom in my exponent. And I can simplify this here. I can reduce it as much as I can, whatever you like. That just becomes x to the 4th, if you can. And then from here, then we say, well, now let's deal with this one here. That's the square root, so that's really a exponent of 1/2. So that really becomes x to the 4th over 2. X to the 4 over 2, which really then reduces down to x squared. So this right here, all of that really just becomes x squared, which is kind of fun to think about. Okay, and some other stuff that you will see in calculus. Here it is. Can you simplify this for me? And this is how tough we'll get here in this class. And again, try it yourself if you can. Otherwise, let's do it together here. So first of all, I'm going to get rid of all these little negative exponents here. And the problem one is this one right here. So let's deal with this here. So that means x is going to stay on top. This one here, the x plus 3 is going to go down to the bottom. But now what I get to have a positive exponent of 1/2. This one, that's already a positive exponent of 1/2. So I'm going to leave it as is. But now I got a little problem. I got to add these guys together. So I'm going to have common denominators. The denominator right now is actually a 1. So what is my common denominator? My common denominator is x plus 3 to the 1/2. So now let's put both fractions with this common denominator of x plus 3 to the 1/2. The first fraction will not change, it stays the same. The second fraction now is going to have this. So now I need a little multiplier. So if I have 1 here and I have x plus 3 to the 1/2 exponent, I'm going to have to multiply the top by, and right here, I'm going to multiply the top by x plus 3 to the 1/2. Okay, and if that's the case, I have common denominators now. Hey, this right here, isn't that just going to be a x plus 3? That's it, because 1/2 plus 1/2 gives you a 1. So let's see if this works here. Common denominator is x plus 3 to the 1/2. We get the x from here, plus sign, and then this just becomes x plus 3. So then simplifying a little more, common denominator is x plus 3 to the 1/2, and then on top now we have x plus x is 2x, and then we have ourselves a plus 3. And if it stopped here, that would be great. It doesn't stop here, because this little exponent of 1/2, isn't that really technically a square root? This is square root of x plus 3. Bummer. That means this is a radical in our denominator. There's a radical in our denominator. So we have to rationalize our denominator. So what should we multiply by? We're going to multiply by the exact same thing, because 1/2 plus 1/2 will give me just a 1, and the square root goes away. So let's go with that here. So that means on the bottom I just have x plus 3, right? Because this right here just adds up to give me a 1. On top, I'm going to leave these separate. 2x plus 3, x plus 3 with the power of, or exponent of 1/2. And there it is. There's my final answer to this. Nothing cancels off anymore. And so I'm set. That would be the final version there.